Next type of defects, crystalline defects, is non-stoichiometric defects. Already in previous video we'll discuss stoichiometric defects. In this video we'll discuss non-stoichiometric defects. Non-stoichiometric, that means what? The ratio of number of cations and anions are different. In stoichiometric defects, the ratio of cations and anions both are the same, but in non-stoichiometric defects, the ratio of number of cations and anions are different, that are not equal. Okay. The change in stoichiometry does not cause any change in the crystal structure. That means if stoichiometric ratio get change, does not affect on the crystal structure. There are two types of stoichiometric defects. First one is metal deficiency defect. In this case, what happened? This defect possible only those compounds metal that shows higher oxidation state. म्हणजे मेटल असेल आणि तो हायर ऑक्सिडेशन स्टेट जर दाखवत असेल तरच हा कंपाउंड मेटल डेफिशियन्सी डिफेक्ट्स दाखवतो. इन केस ऑफ पॉझिटिव्ह मेटल्स आयन्स आर मिसिंग. इन प्रिव्हियस व्हिडिओ वी ऑलरेडी डिस्कस व्हॉट हॅपन इन दिस केस. दिस इज युअर non-stoichiometric nickel oxide compound. In this case, what happened? Nickel oxide is made up of nickel is carries 2 plus charge and oxygen carries 2 minus charge. This is the regular arrangement of the Ni2 plus O2 minus Ni2 plus O2 minus O2 minus Ni2 plus. But in case what happened? This is the presence of cation of the same metal with higher oxidation state than the missing. In the compound nickel oxide, the Ni2 plus ion is missing, creating a vacancy its lattice site. Here one cation is Ni2 plus is missing and create here vacancy at the lattice site. The deficiency of two positive charges is made up by the presence of 2 Ni3 plus. आता इथे काय झालेलं आहे? Here deficiency of two positive charge. It want to neutralize. Okay, that's why two positive charge here deficiency here. That's why one same nickel atom can present in Ni3 plus and Ni3 plus. This is 2 plus, this is 2 plus, but one extra electron it can lose and it become Ni3 plus. It also Ni3 plus. That's why that is this 2 plus charge can balance by this Ni3 plus and Ni3 plus. Okay, you must remember what happened in the compound NiO nickel oxide. One Ni2 plus ion is missing, creating a vacancy at its lattice site. The deficiency of two positive charges is made up by the presence of 2 Ni3 plus. This 2 Ni3 plus ion at non-stoichiometrical the other lattice sites. That means the ratio of this nickel oxide is 0.97 and oxygen is 1.0 in shown in figure. You must remember what happened. This space is vacant. Ni2 plus cation can leave its position and this 2 plus charge can balance this Ni3 plus. Okay, this is the metal deficiency defect. The second type is metal excess defect. In this case, what happened? In this metal excess defect, what happened? There are two types of metal excess defect. What happened in this case? You can see here. Second non-stoichiometric defects type is metal excess defect. What happened in this case? You can see here, this is a zinc oxide compound. In this case, a neutral atom or an extra positive ion occupies interstitial position. In this case, what happened? metal excess defects, that means this is zinc oxide, zinc, you know that Zn in 2 plus oxidation state and oxygen present in 2 minus oxidation state. It is the regular arrangement of the Zn2 plus O2 minus Zn2 plus O2 minus O2 minus Zn2 plus O2 minus, like that. But in this case, what happened, there are some empty space in this arrangement. In this arrangement, what happened, the one extra positive ion occupies, it may be neutral atom or an extra positive ion. In this interstitial space, one of the positive ion of the same metal of the compound or neutral atom can occupy this interstitial position. Now, neutral, here may be excess neutral Zn atom, or here excess Zn2 plus here also, okay, in this interstitial position. ZNO presents two ways of metal excess defect you can discuss here. First one, what happened in this case? First defect is, what happened, you know that I already told you, metal excess defects, that means what, the regular arrangement of crystal lattice in which the same metal atom of the crystal lattice can insert in this interstitial position, okay. Here atom can insert in this interstitial position, excess neutral zinc atom can trap in this interstitial position, okay, neutral zinc atom at interstitial sites. This is the first metal excess effect, that means total number of cations and anion are equal, but one more here, neutral zinc atom present here, that's why this is metal excess defect. Then second case, in the second case, what happened in the second case? In the second case, zinc oxide is heated, it decomposes as, if you can just heat to zinc oxide and it can decomposes into your oxygen, monoatomic oxygen get converted into diatomic oxygen, and zinc metal can loss of electron, 2 electron can loss, and it carries 2 plus charge and 2 electrons it can loss there. In this case, what happened, you can see here, this is the regular arrangement of this zinc oxide, but in this case, what happened, after the heating, zinc oxide get decomposed into Zn2 plus and 2 electron here, and this zinc 2 plus ion and this electron, one zinc atom can loss 2 electron, so zinc, this Zn get oxidation, zinc can loss 2 electron and Zn can form 2 plus ion, and this 2 plus zinc 2 plus ion can trap in these interstitial sites in a crystal lattice, and also electron can trap in the crystal lattice, okay. So you can simply say that here in this metal excess defect, there are some excess metal ion of the same crystal lattice, and also there trap some interstitial sites in the electron of the Zn2 plus in a crystal lattice. In both the cases, there is non-stoichiometric ratio there, and the formula of the ZNO is, in the both cases, Zn 1 plus X and oxygen is 1.0. You must remember, in the metal excess defect, which types of you have discussed here. There are two types of metal excess defect, when in the regular crystalline solid, zinc atom can trap in the interstitial sites, and second case, in regular crystalline solids, when you can just heat to Zn oxide, it can decomposes and Zn can lose 2 electron and form Zn2 plus ion, and this Zn2 plus ion and electron can trap in these interstitial sites, and the ratio of the both the metal excess defect is ratio of zinc and oxide is Zn 1 plus X and oxygen is 1.0. Then next one, by anion vacancies. Next one is by anion vacancies, or it is also called as a color or absenters. What is this? Anion vacancy or color or absenters. What is this? This type of defects imparts color to the colorless crystal. What happen if any crystalline lattice, when any impurity added in the crystal lattice, and this colorless crystal lattice become color. That means what? This type of defects imparts color to the colorless crystal. Again I revise. By anion vacancy or color or absenters defects, what happen? This type of defects imparts color to the colorless crystal. Example, when you can take here NaCl, you know that this is crystal is colorless, but you can heated this NaCl crystal in the atmosphere of sodium vapor. Then what happen? The sodium atoms are deposited on the crystal surface. What happen? You can simply NaCl is it is the colorless crystal. You can heat it in the atmosphere of sodium vapor. What happen? Sodium metal can deposited on the crystal surface. And what happen? You know that this is the Cl minus Na plus, Cl minus Na plus, the regular arrangement of this NaCl crystal lattice. But you can just heat this sodium chloride in the presence of sodium vapor, and then what happens? Sodium can deposited on this crystal surface. Cl minus ion diffuse to the crystal surface. What happen? Cl minus ion can diffuse on the crystal surface, and Cl minus what happened? Cl minus can diffuse on the crystal surface, and here some vacancies at their regular sites. Here from this side Cl minus can diffuse on the crystal lattice, and here vacancy creating at their regular site. These Cl minus ion can combine with this Cl minus can diffuse in the crystal lattice, and their regular site some vacancies there, and this Cl minus can combine with the sodium metal can deposit on the surface of the crystal lattice. Okay, when this Cl minus can leave its regular sites, and it can combine with sodium metal, and it can form NaCl, and one electron lost there. Okay, here what happened? You must remember in this by anion vacancies. How can generated anion vacancies? What happened? Regular sodium chloride crystal can heated with sodium vapors. At that time what happened? Sodium metal can deposited on the this crystal surface. When Cl minus ion can diffuse on the surface of the crystal lattice, and it can leave its regular sites, and there is a vacancy generated. Okay, then this Cl minus can combine with sodium atoms on the surface to form absenter NaCl. When this sodium metal can combine with this Cl minus, and it can form NaCl and releasing electron from in a crystal. Okay, you must remember what reaction takes place. This Cl minus ion can diffuse in the crystal lattice, and this its original regular sites become vacant, and this Cl minus can combine with the surface of the sodium metal were deposited and form a NaCl, and one electron lost there. Then what happened in this case? One electron lost there, and the electron can diffuse into the, when I already shown you reaction when this diffuse Cl minus can combine with this deposited sodium, and what happened? NaCl is formed and one electron is lost there. Okay, the electron diffuse into the crystal. Here electron is released there, and it can diffuse into the crystal, and occupy vacant sites by anion. The anion vacant sites occupied by electron are F centers or colored centers. That means what? You can simply see here what happened in this case. Here what happened? You can see here first time what happened when you can regular sodium chloride can heated in presence of sodium vapor. At that time what happened? Sodium can deposited on the surface of this crystal and Cl minus diffuse, okay, diffuse ions, and that's why it can lose its original sites, regular sites, and this Cl minus can combine with this diffuse sodium metal on the surface and it can form NaCl plus 1 electron. This electron can again diffuse into the crystal lattice, and again this electron can come here, and this space become vacant. This space become vacant, or you can also say that this space become empty there. And what happened in this case? The electron release diffuse into the crystal and occupy vacant site of anion. The anion vacant site occupied by electron. म्हणजे ज्यावेळी तो इलेक्ट्रॉन तिथे जाईल त्यावेळी तिथला anion बाजूला जाईल आणि ती स्पेस काय होईल? वॅकंट बनेल. यू मस्ट रिमेंबर vacant site occupied by electron are it is F center or it is color centers. That means NaCl shows yellow color due to the formation of F center. NaCl is regular white in color, but after the F center it become yellow in color. And non-stoichiometric formula of NaCl is like calcium oxide Na1 plus X, like zinc oxide, it is Na1 plus X Cl 1.0. Here what happened? How can the compound form a color? Because of the, I again repeat here, why it is called as by anion vacancies or color or F center, because I already told you का आपण NaCl ला काय केलं? हीट केलंय ॲटमॉस्फेरिक ऑफ सोडियम वेपर लॅम्प मध्ये, आणि सोडियम ॲटम्स हा जो आहे तो डिपॉझिट झालेला आहे त्या क्रिस्टलच्या सरफेस वरती. मग Cl मायनस जो होता इथे निगेटिव्ह चार्ज वाला, तर तो क्रिस्टल सरफेस वरती डिफ्यूज झाला आणि क्रिएटिंग वॅकन्सीज ॲट देअर रेग्युलर साइट्स. ओके, ही जागा वॅकंट झाली आणि तो जो Cl मायनस आहे तो डिपॉझिट झालेल्या सोडियम बरोबर कंबाईन होऊन त्याने एक इलेक्ट्रॉन काय केला? परत लॉस केला. तो इलेक्ट्रॉन परत इथे गेला आणि इलेक्ट्रॉन इथे गेल्यामुळे तिथली स्पेस काय झाली आहे? वॅकंट झाली आहे. आणि अनॅनिक वॅकन्सीज आपण त्याला म्हणतो, आणि त्या अनॅनिक वॅकंट साइट्स ऑफ anion they are generated and the anion vacant sites occupied by electron. आणि मग जी स्पेस वॅकंट झालेली आहे ती त्याची जागा इलेक्ट्रॉन घेतो आणि त्याला RF सेंटर और कलर सेंटर असं आपण म्हणतो. तर NaCl shows yellow color due to the formation of F center. In next video we'll discuss electrical properties of solid. Okay, in next video we'll discuss.